The title of my presentation is Evolution from Conventional Planar MOSFET to Advanced Gate-All-Around Nanosheet FET. My name is Ortiz-Conde, and here is my picture. I am coming from Departamento de Electrónica, Universidad Simón Bolívar, Caracas, Venezuela. My emails are the following here. And this is a distinguished lecture from the Electron Device Society. The outline is the following. We will talk about the origins, then the evolution, then the SOI MOSFET, the multi-gate three-dimensional SOI devices, the FinFETs, the gate-all-around nanosheet, or the ribbon FET, or the multi-bridge channel FET. All this name is the same thing. And we will talk about the recent development, and finally the summary. I would like to mention two very good review articles that I recommend you to read. The first one is by C.T. Sah, Evolution of the MOS Transistor from Conception to VLSI. It was published in the Proceedings of the IEEE in the year 1988. Here is a picture of C.T. Sah. This picture was taken in the workshop on compact modeling in the year 2007. Another very good review article is by Hiroshi Iwai, The Centennial of FET and the Silver Jubilee of IWGT, Tracing the Origin and Evolution of Junction Technology in FET. This was presented last year in year 2025 and is a very good review article. And here is the picture of Hiroshi Iwai, who is an EDS eminent lecturer. This is the obituary of Professor C.T. Sah. This is taken from the Electron Device newsletter from October 2025. He is the co-inventor of the complementary metal oxide semiconductor CMOS device and the grandfather of MOSFET model. He peacefully passed away on 5th of July 2025. He and Frank Wanlass co-invented and demonstrated CMOS in the year 1962. Here we have C.T. Sah with a wafer, and here we have very old picture when C.T. Sah was very young, and this was in the group of Shockley. He worked for the company of Shockley. The famous Kahng and Atalla model is 60-year-old and is still being cited according to Scopus. The article is by Kahng and Atalla. The title is Effect of Diffusion Current on Characteristic of Metal Insulator Semiconductor Transistor. It was published in Solid State Electronics in the year 1966. And here we have the citation. In the vertical axis is the number of citations. In the lateral axis is the year. So we see that at the beginning, around 1970, it has only about 5 citations per year. But suddenly in year 2005, it starts to increase. And there is a peak here of 40 citations in year 2008, 2007, and now decrease again the citation, but the citation is still around 10. In 1926, the idea of the MOSFET was presented. It was a patent entitled Method and Apparatus for Controlling Electrical Current by Lilienfeld. Here is the device that he proposed. This device is a little bit difficult to understand because it's not very well explained. Here we have a picture of Julius Edgar Lilienfeld. And here we have the same idea, but now it's a new drawing, a new figure by EY, and this figure is a lot better explained. The idea is we have an aluminum foil here. The aluminum foil is contacting copper sulfide, which is a semiconductor. So the yellow is a semiconductor p-type. Here the blue is copper, which is a metal. So we have contact here, and we have a rectifying or Schottky contact here, and this is the idea of the MOSFET. 1928. Now we have the idea of the depletion MOSFET. It was presented by Lilienfeld, and that was a patent entitled Device for Controlling Electric Current from 1928. This is the device that Lilienfeld presented. You can find this in this website. And here we have a new figure by EY. this new figure is better explained than the previous figure. So we have in yellow a semiconductor p-type, we have in blue aluminum, we have here in white oxide, and the idea is with the gate you will control the depletion of this region. So this is the depletion MOSFET. Now we have 9035, the idea of the double gate MOSFET. This figure is presented by EY and is an improvement of the original figure from 1935. We have here an electrode, metal, we have oxide, we have here semiconductor, oxide, and here we have metal. Here we have Oscar Heil, who presented this patent, and then the patent was entitled Improvement in Ore Relating to the Electrical Amplifier and Other Control Arrangement and Devices. It is a British patent from 1935. Now we get to 1947, and the first transistor was fabricated by Bardeen and Brattain. This is the first transistor, and they were really trying to fabricate a MOSFET, but they fabricate this device. Here is the patent. The patent is by Bardeen and Brattain, and is from 1948, and this is the idea, is a semiconductor with two metal contact very close. This semiconductor here is the base, this is emitter, and this is collector. And here we have a picture of Bardeen and a picture of Brattain. It is interesting, the following sentence: Bardeen and I were simply trying to make a good field effect device, and as a result, we were put in a position to observe for the first time a phenomenon now called the transistor effect. What this means is they found that this device was able to amplify, but they didn't understand what was going on inside. Here are the references by Bardeen and Brattain, the two references, the patent and the published article. 1948, the bipolar junction transistor was invented by William Shockley. It is interesting to mention that Bardeen and Brattain were working in the same group, and they fabricated the first point contact transistor. William Shockley was the boss of that group, and 6 months later he came with this idea. The idea is the original, or the idea is the present bipolar junction transistor, and the patent was called Circuit Element Utilizing Semiconductor Material. Here is the patent. Here we have a picture of William Shockley. Bardeen, Brattain, and Shockley received the Nobel Prize in 1956 by the invention of the transistor. Shockley said the following: "What I say about myself, and I am sure most creative people will say the same thing, is that when we look at how long it took us to get certain ideas, we are impressed with how dumb we were, on how long it took us, and how stupid we were. But we have learned to live with this stupidity and to find from it what relationship we should have seen in the first place." Here are the references. This IEEE Transaction Electron Device article is very interesting because it was written by William Shockley in 1948, and he said he summarized in that article all what happened about the invention of the transistor. According to Riordan, the most important invention of the 20th century was conceived not just once but twice. Here is a patent of what will be a point contact transistor. Here is the reference. In Paris, two German physicists, Herbert Matare and Heinrich Walker, built a point contact transistor in June 1948. Here is a picture of Herbert Matare and Heinrich Walker. Now we get to 1960, the fabrication of the MOSFET. Here we have a figure of the first MOSFET. We have the aluminum gate, we have here source, we have here drain, and the channel is here. This is an improved figure by EY, and here is the reference, Kahng and Atalla, published in IEEE Solid State Device Research Conference in 1960. Here we have a picture of Kahng and a picture of Atalla. Now we get to 1963, and here is the invention of the CMOS circuit. Here is the patent by Wanlass and Sah. Here is the idea. This is the original figure. Here we have a picture of Frank Wanlass and C.T. Sah. Here are the references. This is the article in IEEE Solid State Circuit Conference, and this is the patent in 1967. It was granted. We have here innovation used to continue scaling, and here we have 6th generation of Intel transistor. In year 2003, the technology was 90 nanometer, and they start to use strained silicon. In year 2007, the technology was 45 nanometer, and they start to use high-K metal gate. It is interesting to mention that the first transistor was using metal. At that time, it was aluminum, 1960. And then, a few years later, they start to use polysilicon gate because the cell align process. And now, year 2007, they are using again metal gate. Then, year 2011, they start to use FinFET. Here we have the FinFET. Here we have the reference. This was presented, this article in the year 2017. A strained silicon transistor is used commercially in year 2002. In 1951, Bell Labs discovered that stress influenced the mobility in diode. In 1992, Welser from Stanford fabricated MOSFET with a stress silicon channel which present a 70% higher mobility. In year 2002, Intel used a strained silicon transistor in the 90 nanometer technology. There is a book and a review article dedicated to strained silicon MOSFET. Here are the references. Year 2007, high-K metal gate transistor. The first MOSFET in the 60s were fabricated using metal gate. In 1968, Bell Laboratories proposed to use polysilicon gate in order to obtain a cell align process. This became the standard process up to year 2007. In 1998, simulation of high-K metal gate transistor were presented in order to eliminate the polygate depletion effect and to reduce tunneling leakage current between the gate and substrate. This work was done by Hewlett-Packard in collaboration with universities in California. In 2005, Mishrat et al. Predicted that high-K dielectric material will be part of the mainstream technology. They recently reviewed the high-K dielectric development. Here are the references. Year 2007, the high-K metal gate transistor. In 2007, Intel used high-K metal gate transistor in a 45 nanometer technology. Here is the abstract that they presented, and some interesting part of this abstract are the following. In mid-90s, Intel and other major chip makers saw the saturation of capacity in the use of silicon dioxide gate insulator. Several dielectric candidates have been identified and tried, but the results were discouraging. Intel has finally developed their metal gate transistor with hafnium-based material. Here are the references from 2007. Why do we need new transistor structure? This is a good question. Leakage current occurs in the silicon away from the channel. Here we have a conventional MOSFET. The conventional MOSFET is here. Here is the channel, and we have that the body is very thick. On the other hand, the body in the SOI silicon insulator MOSFET is very thin. Therefore, the leakage is smaller in SOI devices. Here we have an SOI MOSFET. The SOI MOSFET is here. This is the body. This is very thin, and the silicon is on top of an oxide. Here we have a very good presentation by Professor Su-Jae-Kin Liu from Berkeley. The title of her presentation is FinFET History, Fundamental and Future, and it was a short course in the Symposium on VLSI Technology in year 2012. You can download her presentation using this link presented here. Here we have an SOI MOSFET presented in this figure. Here we have an N region here is a P region, here is a gate, here is an oxide, here is an oxide again, here is a substrate, the silicon substrate, and here is another gate. The original motivation for SOI MOSFET were suppression of latch-up, greater immunity to radiation, and the possibility of three-dimensional integration. Here we have some references. SOI MOSFET. Research on SOI MOSFET started in 1980 with the fabrication of laser recrystallized polysilicon SOI MOSFET at Texas Instruments. The double gate SOI MOSFET was proposed in 1984 and it was fabricated in 1989 by Hitachi. This device contained the essence of the FinFET. Single crystal fully depleted SOI MOSFET were fabricated in 1987 using CMOS at Hewlett-Packard. Here are the references. Now we will talk about the FinFET. In 1998, the first FinFET was fabricated by Hisamoto from Hitachi in collaboration with University of California at Berkeley. In 1999, IBM selected SOI for their next generation microprocessor. In year 2003, Infineon developed nanoscale FinFET for low power application. In year 2005, IBM, Sony, Toshiba developed a 64-cell processor in 19 nanometer SOI technology. In year 2012, Intel used fully depleted FinFET in the 22 nanometer technology with high-K metal gate and channel strength technique. In year 2024, Hisamoto reviewed the development of FinFET in a very good article. Here are the references. 1989, the Delta SOI MOSFET. The Delta SOI MOSFET was proposed by Hisamoto from Hitachi in 1989. Here is the device, here is source, here is drain, this is the semiconductor, the conduction is lateral, the gate is going like this, the gain is going like a FinFET, the current is going in this direction. It is in essence a DG MOSFET and it contains the essence of the FinFET. Here are the references. 1988, the first official FinFET was fabricated at Hitachi in collaboration with UC Berkeley. Here is the drawing. Here we have the silicon, we have the gate going to three sides. Here is the reference. And a good presentation review of FinFET history can be found in this link over here. In 2012, Intel used fully depleted FinFET in the 22 nanometer technology with high-K metal gate and channel strength technique. Here is a picture of the FinFET. Here is the reference. Now we will talk about the gate-all-around FET, or surrounding gate transistor. That was the original name given in 1988 by Takato et al. From Toshiba, who fabricated the first gate-all-around, and they refer it as a surrounding gate transistor. Here is a picture of the transistor. It is very important to mention that it has vertical conduction because the drain is here, the source is here, this is the semiconductor, in black here is the oxide, and this is the polysilicon gate. So the conduction is from here to here, like this, vertical conduction. Here we have a photograph of the device, and here we have the reference from the year 1988. In 2017, IBM, Samsung, and GlobalFoundries fabricated a gate-all-around transistor composed of vertically stacked nanosheets with the current flowing horizontally. Here we have a picture of that. This is a silicon, so the conduction is perpendicular to this plane, and there is one silicon on top of another, and the gate is all around. The gate is all around here. And here is another picture. So the conduction is in this direction. This is the silicon channel. Here is the reference. It is important to mention that this is a collaboration of three big companies, IBM, Samsung, and Global Foundry. So the fabrication of these devices are very, very expensive. Multi-bridge channel MOSFET, MBC FET. In 2003, Lee et al. From Samsung fabricate the MBC FET. It is a gate-all-around FET with nanosheets stacked vertically and the current flowing horizontally. Here is a picture of the devices, well, the drawing of the devices. So here we have the nanosheet. The conduction is in this direction. Here is another picture. So we have the channel and the gate is all around. Here we have a photograph of the device. Here we have the references. An MBC FET, or gate-all-around transistor, is composed of vertically stacked nanosheets with the current flowing horizontally. Here we have a drawing. Here the gate is all around. And here we have the nanosheet. The conduction will be inside this plane. Here we have a cut across the source drain region. And so we have here will be a contact. This is source or drain. This is the other contact. This will be source or drain. And the nanosheet is going like this. And the conduction is in this direction. And the gate is in blue here, all around. Here is the reference in which I took these two drawings. Here we have the three-dimensional schematic view of a simulated gate-all-around transistor. Here is the 3D schematic view. So we have here source, we have here gate, here we have drain. The nanosheets are going like this. The gate is all around. Here we have the YC plane two-dimensional view. So we see here in green is the nanosheet. In yellow is hafnium dioxide. And in pink is titanium dioxide. So these are the two dielectric. And the conducting metal is in red all around. This is the gate. So we have here the XY plane two-dimensional view. It will be like this, source here, drain here, the nanosheet going like this. And it is important to say that the contacts are on top in both cases. Here we have the reference. Now we will talk about parasitic resistance in gate-all-around transistor. This is very important in modern devices. Here we have a drawing. Here we have the channel here in blue. These are the nanosheet. And here we have the contact to source. And this is the contact to drain. So we have a resistance due to a contact metal semiconductor. We have a resistance about this semiconductor region. And this resistance is not, has different values for the different channel. For example, here it will be smaller, and farther it will be larger, the resistance. Here we have the reference from which I took the view graph. 2017, the fourth sheet. Here we have a typical FinFET. We have an N-channel device here and a P-channel device here. Here we have a nanosheet. We have an N-channel here and a P-channel here. And here we have the new structure, the fourth sheet. The fourth sheet has this shape. So the fourth sheet has a smaller area. There is a dielectric wall between the P and the N-channel FET. Here is a dielectric wall. The gate is around 3 sides with the 4 next to the dielectric wall. We see here the gate. The gate is only 3 sides. And here is the dielectric wall. Here are the references. So the importance of this device is it has a smaller area. Now we will talk about the vertical transport nanosheet FET, VT FET. In year 2021, IBM and Samsung presented a vertical transport nanosheet FET BT FET featuring horizontally stacked nanosheet with vertical current flow. In previous lateral transistor, the gate, source, and drain contact are positioned side by side. In a BT FET, one contact is moved to the bottom of the stack, which significantly saves area. Here we have a drawing, and this is a device. We have here the top electrode. Here we have the nanosheet. The nanosheets are horizontally, and the conduction is vertical in this direction. So let's say, for example, that this is the source. Is the contact here in the bottom electrode. This is the top electrode. Of course, you may also do a contact on top, but this contact on top will be for many transistors. Here are the reference, and it is important that we mention that this device is under research and maybe in a couple of years could be a commercial device. Kahng and King from Samsung wrote the following: I want to emphasize the importance of focusing on fundamental values and make relentless effort to change ourselves, turning challenges into opportunities. Despite nearly 50 years in semiconductor industry, I feel there is still a long way to go. Here is an interesting plot that he presented in his article. Here we have the year in the horizontal axis, and we have the different devices and the different advances. For example, planar until year 2005, then the high K metal gate transistor, silicon germanium, then we go to FinFET in year 2015, and then we go to nanosheet in year 2024. This is taken from reference 2, and here are reference 1 and reference 2. The gate all-around MOSFET inspired the nanowire device. Here we have the gate all-around. In blue is silicon, in white is oxide, in green is the gate. So if this structure is repeated and one put on top of the other one and one on top of the other one, so we have what this is called the nanowire. Nanowire because this is almost a square. Here is the reference. The FinFET and the nanowire inspired the nanosheet device. Here we have the FinFET. Here we have the nanowire, and this is the nanosheet. What is the main difference between the nanosheet and the nanowire? Here the semiconductor is a square. Here the semiconductor is a rectangle. And here is the reference. Here we have some interesting data from Stacy Smith from Intel, and this data was published in year 2017. It was available in this link, but it's not available anymore. Here is the data. Year 2002, there were 25 companies with leading-edge technology. Year 2004, there were only 18. Year 2006, there were only 13. Year 2010, there were only 8. Year 2012, there were only 5. IBM, GlobalFoundries, Samsung, TSMC, and Intel. Year 2014, there were only 4. GlobalFoundries, Samsung, TSMC, and Intel. I guess the reason because this presentation is not available anymore in this link is because this presentation was from Intel, and year 2014, Intel was one of the four companies with leading edge technology, but you will see what happened. Here, if you want to find this plot, you can also find this plot in the presentation from Frank Scherz, Past, Present, and Future CMOS Scaling, an Academic Perspective on year 2021. This presentation is available in this link, and this is a very good presentation. Updating the previous plot. In 2016, we have 4 players: Intel, GlobalFoundries, TSMC, and Samsung. In 2019, there were only 2 players working with the 5 nanometer node, TSMC and Samsung. TSMC 2nm technology entered production in 2025, and the technology S16 1.6 nanometer node is scheduled for production in 2026. Samsung announced in December 2025 the first processor CMOS 2600 built on a 2nm technology. Intel has been outsourcing to TSMC during the last 2 years in order to remain competitive. Now they are starting production of 18 angstrom node in February 2026. Here are the references. Now we will talk about the international roadmap for devices and systems. Here we have the scaling scenario for device architecture. Here we have the bull device, the classical bull device. These are planar devices. Then the evolution was to a partially depleted SOI MOSFET, in which this is a thick region. The semiconductor is a thick region. Then the fully depleted SOI, in which the semiconductor is a very thin region and is on top of an oxide, and then the substrate silicon. Then we go to the bulk FinFET. Here we have the semiconductor in green, and this is bulk because the semiconductor here is connected to the bulk device, to the wafer. Then we have the SOI FinFET, so we have here a FinFET, but this FinFET is on top of an oxide. And then the evolution was to the gate-all-around device, which nowadays is lateral. The lateral could be bull device here, or could be the semiconductor on top of an oxide, and it will be an SOI lateral device. And the next device could be the vertical device, in which the conduction is vertical, and it could be bulk or SOI device. A prediction from 2019. In 2019, Malinowski from GlobalFoundries predicted that FinFET technology will be dominant until 2021. He was right. This decade of FinFET will be finished because of technology challenges. He was right. In addition to the enormous cost of manufacturing and technology development, the IC design costs are also increasing with the new node. For example, 29 nanometer costs 50 million, 7 nanometer costs 300 million, 9 nanometer 500 million. After 2025, classical CMOS technology and Moore's law will end. I think he was wrong. Graphene and carbon nanotubes are not planned in CMOS mainstream manufacturing in the near future. I think so. Here is a reference. Gate-all-around transistors are replacing FinFET. Samsung presented a 3 nanometer gate-all-around static RAM in 2021 and began chip production in June 2022. TSMC moved to gate-all-around for the 2 nanometer node. Intel is using the gate-all-around transistor with the name of Lilienfeld. IBM is also working with the gate-all-around transistor. And here are the references. Recent development. TSMC 2 nanometer technology entered production in year 2025. It is using nanosheet transistor. The 1.6 nanometer node is scheduled for volume production in year 2026. TSMC Arizona first fabrication is in production of 4 nanometer technology since year 2024. TSMC has also started the construction of a second fabrication, which is scheduled to begin production of 3 nanometer process technology in year 2026. The investment will be $40 billion, representing the largest foreign direct investment in Arizona history. Samsung announced in December 2025 the first mobile processor CMOS 2600 built on a 2 nanometer gate-all-around transistor architecture. Intel has been outsourcing to TSMC during the last 2 years in order to remain competitive. Now they are coming back to the competition. They started production of an 18-angstrom node in February 2026. Here are the references. Here we have an important contribution by Intel. It's a three-dimensional stack NMOS on a PMOS nanoribbon, and it was in year 2020. Nanoribbon is the name that Intel used for the gate-all-around technology. Here we have the planar technology. We have a P-channel transistor here and N-channel transistor here. Then the evolution was to FinFET. So we have here the P FinFET and here the N-channel FinFET. And then the evolution was the nanoribbon. We have a nanoribbon here and a nanoribbon here, or gate-all-around. And then what Intel is proposing in year 2020 is to take one transistor on top of the other one. So here we have the P-channel device, and on top of it we have the N-channel device. Here we have a photograph of the devices. Here is the PMOS, here is the NMOS transistor, and here we have the transfer characteristic of an inversor using CMOS circuit. Here is the reference, IDM, year 2020. Year 2021, IBM and Samsung presented the BT FET. They presented the vertical transport nanosheet BT FET as a possible device for future nodes. There are nanosheets stacked horizontally with the current flowing vertically. The vertical transport nanosheet architecture presents an opportunity to reduce area. Here is a drawing of this device. Here is a photograph of this device, and here is the references. Year 2026. There is a calculation of the asymmetrical parasitic series resistance in vertical nanosheet FET. Here is the reference, year 2026. Here we have a plot of the drain current as a function of gate bias in the normal mode in red and in the reverse mode in black. And we see that there are a strong difference between the normal and the reverse mode. The constant current extrapolation method presented in 2, here is a reference in 2, this is a paper by our group and it was done in February 2020. The constant current extrapolation method to extract the difference in RS and RD, this is called delta R, is basically in this method. You will plot delta VG as a function of ID, and you will have an slope which is delta R. So delta VG and delta VT are the difference in gate bias and threshold voltage respectively between normal and inverse operation mode at a given ID. So if you plot delta VG as a function of ID, it will get a straight line. The slope is delta R. This is because of this equation, delta VG. Delta VG is the difference between the gate in the normal and inverse mode. So you will plot delta VG as a function of ID. It's in a straight line. From the slope you get delta R, and from the slope delta R is RS minus RD for 100 ohm. On the other hand, you can also calculate BDS as a function of ID. BDS as a function of ID is the parasitic series resistance plus the resistance of the MOSFET, which is this one. So if you plot that, BDS as a function of ID as a function of BGS, if you start to increase BGS, it will go to the limit in which the dominant resistance is the parasitic resistance, and this is negligible. So by doing BGS going to infinity, BDS divided by ID is just the parasitic resistance. If you do that, you estimate the parasitic resistance is equal to 800 ohm. So if the summation is 800 ohm and the difference is 400 ohm, you combine both of them and you will get that RS is 600 ohm and RD is 200 ohm. IBM and Samsung proposed to replace copper by ruthenium. So when I see this name, ruthenium, I don't know what is that element. So I have to go to a periodic table and find here ruthenium. Ruthenium is this element and copper is here. Copper is a metal. I knew copper. I didn't know ruthenium. I am starting to know ruthenium. Here is the reference. So it is important to mention that the chemistry is very important in the fabrication of modern semiconductor devices. Here we have the recent trends in Intel. Here we have a plot in which we have year in the horizontal axis, and in the vertical axis we have the length. So let's start here with the gate length. The gate length was decreasing in the year 2000, but nowadays, year 2020, 2025, is not decreasing is decreasing very little. And then we have here the contacted poly pitch, CPP. The contacted poly pitch was decreasing in year 2000, but nowadays it's not decreasing anymore. It's almost stable, it's almost constant. So therefore, the contacted poly pitch is not decreasing presently, and the gate all around is expected to allow another 10% of gate length scaling. So this is what is expected. So now we have here years in the horizontal axis. Here in the vertical axis we have the length, and we have the metal pitch here, which is not decreasing anymore, and the library cell height, which is decreasing a little bit because of the better designs. The library cell height is decreasing, metal pitch is not decreasing, and here we have the reference. Conclusion. We have reviewed the evolution of MOSFET. FinFET were the dominant CMOS device architecture throughout the last decade. The FinFET is being replaced by the gate-all-around nanosheet transistor. Vertical transport nanosheet (VTFET) technology is being researched for its potential to reduce chip footprint. I would like to dedicate this presentation to the memory of my parents, Alicia Cristina Conde Brandt and Adelmo Antonio Ortiz Piñero. Es una honra visitar virtualmente o Brasil e eu realmente agradezco este convite. Será un placer enviarle una copia da minha apresentação se você solicita por email ortizc@ieee.org.